Welcome back to Grad Prob Prog, Lecture 22, RL is Inference. I'm Frank, this is UBC. Great, cool. Last time we did meta learning in a disastrous lecture, which I almost don't want to put on YouTube because, I think everybody sort of got lost, which is really, again, too bad. I highly encourage you to go back and look at the lecture notes on that. But the high level of things that you should have taken away is that, meta learning and amortized inference, they're very, very similar. They're basically the same thing. In particular, in models where you have IID observations in a fixed environment, which is a subset of the use cases for meta learning and probabilistic programming. We talked about neural processes, conditional neural processes. We kind of skipped over MLPIP, but it's much of a muchness, really. And amortized probabilistic programming inference are fundamentally, they're all the same thing. The one little trick that I tried to highlight was that of replacing the sequentially updated posterior, basically refactorizing the joint distribution in the variational objective with a different factorization that had a sequentially updated posterior that then was replaced with a variational approximation, which is a neat trick. And it kind of gets towards the perspective that there is some loss that has some reconstruction terms and has some whatever, and you can mix and match between inference networks and generative models and build very complicated and interesting losses. Today, we're going to do reinforcement learning. We're going to touch on reinforcement learning in one lecture, but we're going to do it from the inference perspective, which I think is a very valuable perspective and one that's being picked up on in the reinforcement learning community a lot now. So lots of RL is being formulated in this way, modern algorithms and whatnot. How many of you are familiar with RL in general? A little bit? Okay, cool. How many of you are familiar with the inference perspective on RL? A little bit. How many of you read the lecture notes before lecture today or looked at them? And those of you who know something about the RL as inference perspective, did you get it from those lecture notes or from somewhere else? Okay. So there's I think it's referenced in here. If it isn't, I just want to put it right up front. So we put together some notes, which are, I think, in some ways more complete than, well, they're whatever. They're compatible with a tutorial paper written by Sergey Levin in 2018 on RL as inference. And Sergey did the field a favor by writing down a bunch of stuff that kind of a lot of us knew but hadn't bothered to write down. And this is this inference perspective on RL. So, what is RL? For the few of you who are not familiar, it's an area of machine learning concerned with intelligent agents and how they act in environments in order to maximize some notion of cumulative reward, right? You can argue that RL is one of the basic machine learning paradigms alongside supervised and unsupervised learning, and there are some things that are different about RL. In particular, how you gather training data, like the data gathering process is coupled to acting in the world, and that makes it different to the others. The general goal of RL is to learn policies. So a policy is a thing that tells you, given that I'm in a particular world state, how do I act, right? I'm in the middle of a graduate class lecture. What do I do? So it's about learning policies or controllers that maximize reward. And the framework, the straight up RL framework is super general, right? And it encompasses lots and lots of concepts from classical control to artificial general intelligence. And it's a huge field. I mean, there are thousands and thousands of papers, and I, amongst the members of my group, a couple work on RL, but the people who work on RL have an even harder reading list comprehension task than even most people in machine learning writ large, which is hard. So a couple of things. So one is RL is super inspirational. Everybody knows about the playing Atari via RL and the DeepMind successes there. And the setup is like, how do we learn an agent or policy that, given a frame of or the interpreter state, actually in some cases, of an Atari game, like give me a frame, learn a policy that learns to press buttons in a game-specific way that maximizes some notion of reward, which generally speaking is not dying and maximizing score. And those two things are kind of equivalent, right? This was arguably the first effort to really take RL seriously, because there is a little bit of a, I should just say this straight away, for reasons that are compatible, that are kind of the same reasons that that inference in higher order probabilistic programs or inference writ large is very hard. This same problem means that RL is still outside the bounds of being practical. But you can play Atari games. And you can learn to control things that would be difficult to write down classical control algorithms for. So Mujoku is another control suite that's very popular, but these happen to be images from the DeepMind control suite. And the question is, how do we learn an agent or policy that walks without falling down, or hops and makes progress, or moves by choosing actions in general, changes in joint positions, or some other parameterization, torques at every time step that maximizes an expected reward, where the reward here might be how far does the agent go, or does this ball go into the cup and at the end, and how many swings does it take to get there? So like some distance traveled or final objective achieved in a minimum number of steps, or controls applied, so on and so forth. And of course, there are papers like Learning to Drive in a Day and these sorts of things where people are trying very unsuccessfully so far to apply reinforcement learning to applications like autonomous driving and these sorts of things. In other words, how do we actually control a vehicle so as to maximize some notion of reward? And I'm not going to get into, well, until the end, when we probably have a little bit of a philosophical discussion. But one of the difficulties in reinforcement learning in general is to even decide what a reward should be, or what a reward for a particular task is, right? And even the RL as inference perspectives gives you a little bit of a handle on why this is. Another way of thinking about why this is both important and hard to do. So the formalism in which RL is posed is that of Markov decision processes. And a Markov decision process is a generative model of a time sequence, tau. Okay, it's a sequence of tuples. So every element of tau here is at some particular time step generally. And at that particular time step, there's a tuple of things, which are the actions at that time. So this would be AT, ST, and RT. Now, note, we're deviating from graphical model notation here ever so slightly, which is to say you can either think of this RT as being Dirac distributed, or this is just calling this out as a deterministically computed node, a node computed deterministically from the values of ST, AT, and in this particular case, ST plus 1. Okay, but there's some process that generates these tuples. Each tuple consists of a state. So the state can be where you are in the world, your physical configuration, your velocity, the car, car accelerator state, the fuel consumption rate, whatever. It's the state of the world. Some action. This could be a button. The state in the Atari game is is a little complicated to describe, but really the state there would be the process state of the Atari game. And an action there would be which button to push. An action in the self-driving car case would be what accelerator or steering control to apply. And some sort of reward. And the reward here is very, very much in the eye of the beholder. But it's generally some signal as to whether or not the instantaneous action is important. And generally speaking, at the very, very end of a task, depending on how you set it up, there may be some reward at the end that says success or not. So you might have 0, 0, 0 all along here for rewards, and then some success reward of like 100 if you get the ball in the basket. Or there could be negative rewards for having to walk through a maze. Negative, 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 negative. There's a cost to go, and then you achieve your goal. Or there's some positive reward accrued for every step that you take, and you want to maximize the distance of the number of steps that you take before you fall over, or whatever. These rewards can be lots and lots of different things, okay? And of course, there's some notion of what's allowable, what actions are allowable in each state. So in Atari, the actions that are allowable are the same in every state, right? So you could just break this state dependence. But there are certainly, when you're doing Mijoku or something like that, and you're applying direct limb position commands, like where to put limbs, right? There are going to be allowed actions that are physically, there will be actions that are disallowed by physical constraint, right? Either torques that cannot be applied because you're already applying maximum current, or you can't actually move your arm through your body, so you can't make particular displacement actions, okay? So this is why we have this in the general setup, state dependence on what actions are allowed. You may have heard of, and I've written a number of papers about partially observed Markov decision processes. The partially observed Markov decision processes and MDPs are pretty closely related. I'll try to say what's on this slide without referring to this slide, but we'll go to it and say, in partially observed Markov decision processes, the state of the world is not fully observed. That's really the main difference. In other words, the state of the world is evolving all around you. One way of thinking about it is that you have a foveated view of the world, but stuff is happening behind you that you can't see. It's still happening. The world is still transitioning, but you can only observe a part of it. Or if you were playing checkers and you can only observe a 3x3 patch of squares, and you have to figure out what else is going on in the game and still be able to win. Another way of thinking about it is in Atari. There's a random number generator out there that's throwing in characters from the outside world. You can't actually see, you don't have access to the full state. Even looking at the screen, you don't have access to the full state of everything. Like in particular in Montezuma's Revenge or something like that, where you can actually change the state of the world by acquiring stuff and putting it in a pocket that you can't see, right? There's partial observability, okay? Otherwise, the setup is more or less the same. There are actions that you can take in particular time steps. This is AT. The things that you can see, the projections of the state are OT, the state is ST, the reward for whatever you have before is that. And the way we write about this is that there's a belief state as well. And this thing I'm not going to go into in this lecture, but it's a very, very interesting thing to think about. But effectively, your actions now cannot be dependent on the state. They must be dependent on something else. And in particular, the way you would think about acting is you would act. You know how to act in particular states of the world, but you don't have access to the state of the world. You can only get samples of the state of the world, or a belief or a distribution over the states of the world, given everything that all the observations and actions you've taken up to that point, right? So this part of this Markov chain, or this stochastic process, actually involves an inference task. So there's actually an inference task running on this edge. And in general, the belief state is deterministically computed based on all of the previous belief state, and in particular, the latest observation and action. Okay.
Can I ask a quick question?
Yeah.
So why does the belief and state needs to be separated? Like, can't you run inference on what state you are in and then use it to guide the policy instead?
That is one way. So if you run inference about the state, so basically it's very complicated. This is one I don't want to. This is a rabbit hole I don't want to go down in this lecture, but it's a very interesting thing to think about. One way to frame control in POMDPs is to frame your action selection as acting on the outputs of an inference algorithm. Yes, but from a graphical modeling perspective, that's what this belief state represents. That's exactly actually what's happening. You're integrating information about your preceding belief state, which is updated by your observation and by your action. And it's the accumulation of this information within the context of the model, the underlying MDP model, that gives you your belief state. And of course, you select your action based on your belief state, but that belief state is a distribution over states. Okay.
Can I ask something here as well?
Yeah, please.
If you leave out the belief state here, like, do you end up with anything that's sensible to the model at that point? Like, or are you just like making sort of like random guesses at every step based on your previous observation?
The issue, and actually, I'm very happy that we have this belief state in our way of looking at this. The issue is that if you don't have the belief state, then if you see POMDPs, sometimes you will not have this belief state bit on them, and then the actions just appear out of thin air. They're just they arrive from some extra model thing, right? But what do those actually depend on? If you actually look at what they depend on, whatever your belief is, the only thing that they can actually depend on are all of the actions and observations, because that's all that you have, and they depend through the model, right? But so in other words, whatever your belief state is at this time step, right? It's been updated with whatever observation you have, whatever action you have, and there's some inference that's happening, right? And this is the craziest link function we've talked about in this course by far. This link function is run inference in the entire graphical model.
Right. Yeah.
And oh, by the way, just for the fun of it, if you run inference in the whole graphical model, because this happens to be a state space model, you can run sequential Monte Carlo and keep your partial state information up to date so that you can do one-step updates of your belief.
You don't have to start from scratch at every time point. You can just sort of use the results up to that point and just.
You don't have to start from scratch at every time point, that's for sure. And it would be, but in theory, that's what you're doing, but you probably don't want to do that because it's going to be computationally inefficient. Okay. In practice, what people do is they reduce POMDPs to MDPs by saying that the actual dependence, like what this thing is actually dependent on if you run deseparation in this model, are the actions that you selected and the observations that you had, in which case you can just write this thing as a function, a nonlinear function of a set of actions and observations going back, which in theory should go back to infinity, go back to the beginning of time, whatever that is, right? But in fact are cut off to be a finite set because whatever RNN structure you're going to use anyway is going to forget. So it kind of doesn't matter, right? Okay, that's basically what I say here, but yeah, so we can skip that. So reinforcement learning is about learning a policy or controller that maximizes expected reward. Okay, so the reward, again, in this particular setup, you'll often see this without the st+1 on it. It doesn't really matter. The reward can be a function of whatever. But the critical part is that the expected reward is an expected reward with respect to some distribution, which we'll call Q, pi, phi. Okay, and that's a whole lot of stuff, but you'll understand why in just a second. So this expectation is over trajectories, and you've already defined the trajectory as being the set of a time sequence of tuples, STAT-RT, STAT-RT, blah, 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 right? Generated by acting in the world. So this is a little bit different, and you'll see why this is a little bit different as we go. So this is saying if I apply an action in a particular state of the world, I'm going the real state of the world, like Newtonian physics running in the real world is going to make an ST plus 1, right? The only thing that I get to control is the actions that I take, right? And then we're going to use some parametric policy pi phi to do that. So this distribution over trajectories Q is over some. There's two ways of thinking about this. Starting state, if you have a single task that you're trying to solve, or an equilibrium distribution over states, if you're thinking about this in terms of being a meta-learning kind of problem. Then the world transition model, which we will not know, okay? We're not even going to model in this particular case. And a parametric policy, which is a stochastic policy, which is to say that given a particular state, I'm going to have a distribution over actions that I can take. This thing can reduce to an atomic distribution, right? In other words, it can be in this particular state, I always take this particular action, right? One particular action. Okay, so in what follows, right? Somewhat confusingly, we're not going to model this thing, right? And you'll see why this is the case, but you should be aware that we're going to be talking about model-free RL, which is the dominant paradigm right now. And by model-free, what it means is we are not going to model this. We're going to actually sample. The only time we're going to be able to sample from this is important, the only way that we can sample from this is by interacting in the real world where we actually draw real samples from this distribution because it's the real world. Okay. Okay. Now what's funny is, of course, that the real world in most model-free RL setups are simulators, right? They're actually, and we know that simulators are models, so that's a little bit confusing. But okay. So if the goal of RL is to learn a policy that chooses optimal actions to take in each state, then such an optimal policy would have parameters that look like this. We want to basically look at this quantity, this expected reward, expected future reward, expected cumulative reward, and find the parameter phi that maximizes this, which is to say the parameter of this parametric policy from which we're going to choose our actions, our state-dependent actions. Okay. If we wish to use gradient descent techniques to find this phi star, the parameters which maximize the expected reward, then naively we can do what we've been doing all along. We can just use gradient methods, right? So we can take a gradient of the expected future reward under this Q, and we can do the things that we've been doing for the last couple of times. So now all the stuff that we've been talking about is going to come full circle, right? So we can pass the gradient and we can rewrite the expectation as an integral over the path, right? And then pass the gradient inside, right? And then use the log derivative trick that we've done like 6 times. Which is to say that this and this are equivalent, right? And we can rewrite this as an expectation. By the way, R has no phi dependence, so we can drop the chain rule terms here, right? So now we can rewrite this as an expectation over Q of the score function times the reward.
Can I ask a question here? Is just like it might not be like I'm just trying to think out loud, but like the fact that Q also has this term B S T plus 1 S in it, is that problematic for taking the score and taking this expectation? Or I guess for the derivative it doesn't really matter, and for the expectation.
So let's be clear. So we're just this is good. We are going to be talking about in this particular case we're going to be talking about MDPs only. So we're not talking about POM-DPs, first of all. So no POM-DPs. We're talking about MDPs, even though we talked about POM-DPs. So this is probably not clear in the transition. So we're going to be talking about MDPs. The thing that I didn't say out loud, just to be clear, in practice, many POM-DP RL setups assume BT to be Dirac distributed about some nonlinear function of this. And if you do that, this reduces the POMDP to an MDP with a stochastic state function. Even if you have a true MDP has a deterministic state transition because it's Newtonian or whatever, if you do this, then basically the POMDP, pushing that into the MDP framework just means the state transitions become stochastic. So like we can just think about MDPs.
But like we don't have access to that directly, right? Like we still need sort of like the real world, whatever that means, to try this stuff.
That's correct. That's correct. Or we have to model it. So I'm saying that we're not going to model it, right? We are going to actually interact with the real world, right? And that's how we're going to get this thing.
Yeah. Okay. Okay.
Okay. So all we're doing right now is trying to learn in the MDP setup, which can accommodate POMDPs if you do this, this reduction thing. All we're trying to do is learn phi. We're going to try to learn phi via gradient methods, right? And this is just the standard, reinforced trick score function estimator thing that we've looked at several times so far, right? And we should note, just to be clear, that the gradient of this thing, the only terms that actually have phi in it are the T policy terms. The rest of them don't have this. Okay. And obviously, based on the stuff that we've thought about in the course so far, just to be clear, right? If your action space is continuous, right, you should probably not use the reinforced trick, but instead should use pathwise derivatives, right, and use the reparameterization, right? But we're not going to talk about that. Also note that if we wanted to actually estimate this this gradient under this formulation, this requires complete trajectory rollouts. Okay. So the only way to compute the gradient is to roll out a whole bunch of times under this, right? There's no, like, literally you have to interact with the environment every single time and roll out a bunch of times. But the tantalizing hint here is that, based on what we've been looking at, this looks a lot like, in fact, almost exactly like the amortized inference math that we've been doing, right? If you think about it, we've even had a little ratio here that was something that we computed for, this thing was some P over Q term where whatever this tau is, this tau looks a heck of a lot like all the random variables in a higher order probabilistic program. It's basically the same thing, right? It is the same thing. Okay. So cool. So maybe we can frame this as an inference problem, right? And get somewhere. And this graphical model is the key to understanding RL as inference. And you can go read the RL literature, and you can go read the inference literature, and there's relatively few people that are working at the intersection, right? Sergey Levin is one, and Peter Abil as a result of their collaborations, us, so on and so forth. Although we work more on the inference side, but whatever. So the idea is we're going to augment the graphical model with some optimality variables. And you can then think of the reward function as just being a link function that produces the probability distribution over these optimality variables OT. Okay? So if we've got the MDP set up, I've dropped this edge. I don't really care about this edge. It's going to be easier to not have this edge just to make the equations smaller. Okay, so the reward only depends on the current state and the current action. It's fine. But there's these optimality variables, and what the heck are these? Okay. So just keep this graphical model in mind. The state transitions, as always, you choose your actions from the current state according to your policy. This is of course pi phi along here. This is P of this is P of st plus 1 given stat, right? And this is just a reward function, right? But now there's this funny thing where we need P of ot given whatever, in particular stat, in order to make sense of this graphical model. Okay. So this is what I said. For convenience, we've dropped the other cross S here. That's fine. So it's the same as an MVP in the previous figure, except we dropped one state dependence in the reward function. And the model is imbued with these always observed optimality variables. Okay, and these optimality variables trip people up, but they're actually really straightforward. They're just contrived. They're contrived auxiliary variables that are contrived in the very particular way so as to cast reinforcement learning as a graphical model in which one can utilize all the inference algorithms that we've looked at throughout the entire course. Okay? So the OTs take value true. This is important. All of these are observed, and they're all equal to 1 or true, depending on your type system. Okay. This is a little bit weird. And I just for the fun of it, I was thinking about it beforehand. You can always think of regression also as always observing 0. And the link function to the normal that computes 0 is the difference between the true value and the predicted. So, like in other words, in a regression problem, if you're doing yt is approximately equal to w transpose x t plus whatever. I'll just go with w transpose x. That's fine. You can think about yt. Like, this is not the quantity that you're observing. You're actually observing 0 with a link function, which is yt minus w transpose xt and whatever, sigma squared. So
some questions here.
Yeah.
I'm trying really hard to follow because I feel like I maybe fell behind, but so maybe these are going to be like dumb questions, but I can't understand why we like this. So this is a graphical model here. Why we would have, so I think RT is like the reward.
Yep.
These are reward nodes. Why would we have an arrow from RT to an observation? We're like, yeah, that's just one thing that I don't, maybe you explained it.
Yeah, so what RT is not a random variable. There's nothing to observe, right? You're not condition. There's nothing to condition on. There's nothing to. It's just something that's produced by the stochastic process, right? There's like a process.
Deterministic function that takes in like a state and then gives you back like a value, I guess.
Yeah. So the only thing that we can do so far, the only operation that we can do is we can say, okay, there is some distribution, and there are some rewards, right? And we can get those rewards by literally adding these things up, right? And the distribution is whatever is down here, right? But this is not something that you can do inference in. This is just something that you can take an expectation, like you have an expected reward, and you have to take a gradient of whatever parameters. You have to optimize this expected reward. That's not a terrible. I mean, you're free to optimize that. That's the classical perspective on RL. The problem is you have an expected reward. Optimize, right? Okay, and I haven't got quite to what this observation is, but what I'm saying is, like, this is the graphical model. Just bear with me, right? There's a graphical model, and we're going to observe that these values are 1, right? And I was trying to relate this to a regression model, where you could think about the regression model as always observing 0 with some link function that, for instance, computes the difference between the true value and your predicted value, right? That's exactly equivalent. There's no difference, right?
So I'm sort of confused about the observations, because like the states are also observed. Like when you're in a state, you know that you're in a state, right? And then there's just some extra thing that you're observing. I'm having a hard time like putting these things together.
That's totally fair. You don't have quite enough to put them together yet. That's okay. Hang with me for maybe 2 more slides, and then smack me if it's not making sense, right? Right now you should be at this stage where it's like, what the F is going on, right? Okay.
Okay.
All we're trying to do is how do we turn the RL problem into an inference problem such that we can deploy our inference algorithms to solve the RL objective.
Okay.
Okay, so you could look at that expected reward and say, I'm just going to optimize that directly. I really want to be able to say, going, like pulling everything together in the entire course and say, look, right, we've got all these crazy ass inference algorithms that you've invested so much time and effort in. Well, give me something that I can actually do with them that's interesting, right? And one interesting thing that you can do with them is solve RL problems. You can solve that optimization problem using any of the algorithms that you've implemented to this point. Okay. All right. So that's an interesting. So that's it's basically saying if you have some optimization problem like this, you can always cast it into an inference problem that you can deploy inference algorithms to solve the same or very nearly the same objective. Okay. And that's a powerful perspective that I'm trying to get across. Right. That's really actually the whole point of this lecture, because you know how to do inference, right? And most of you know how to do optimization. The question is, how do we stick them together? And I talked a long time ago about how like Markov chain Monte Carlo, in particular Metropolis Hastings, is like the world's crappiest inference optimization algorithm. So that's one connection. But here we're saying like there's this funny RL problem that's a really hard inference problem or optimization problem, but maybe we can bring the tools of inference to bear. But in order to do that, we have to turn it into an inference problem, right? Which means that we can't, and you'll see. Okay, so there are these optimality variables. They're always one. And in the sense that we just talked about, like in the regression case, you observe 0. Here we're going to observe 1. Doesn't really matter. And in particular, we're going to say that this fixed value at all time steps of 1. So we'll be fixing the value, but the link function changes. And the link function is state dependent. Okay? So the probability of OT equals 1 given AT and ST is given by exp R of ATST. Done. And of course, probability OT equals 0, this is a Bernoulli distributed quantity, is 1 minus exp R ATST, the exponent of the reward. But it's never used. It doesn't exist. Right?
Can I ask a question?
Yeah.
What if like the reward is really high? Like let's say reward is 10, and then the probability of the optimality being 1 is e to the power of 10?
Good question. Okay, so there's two ways of thinking about this. One is you can either rescale your rewards so that they're specific, their probabilities, or you can not worry about it and you'll see how it works out in terms of interacting with the inference algorithms that we've got. So rescaling your rewards is totally fine, and it has to deal with like we could go into that. But if in order for this to be okay, you really want this to be less than 1, okay, that's great. Put a 1 over a z naught over here and make sure that that's between 0 and 1. Or pass it through a sigmoid or whatever. Totally fine. Okay. And there's from the RL/economics perspective, there's actually quite a literature about these reward transformations and what they actually mean in terms of like people's cumulative regret and discount factors and all. There's a lot of stuff, right? Anyway. Okay. So with this crazy optimality variable, we're going to write down a couple of things. Okay. So in the following, okay, O, when I just write O, it's going to refer to all of the variables because like they're all 1, doesn't really matter. I just want to be able to refer to them. So O equals 1. They're equivalent. They mean the same thing. Okay. So Q tau is as it was before. So Q phi tau is our variational distribution over trajectories tau, right? I've hinted that it's a variational objective. It's exactly the same thing that we had before. It's our rollout distribution. It's the thing from which we are going to sample. It's how we're going to interact with the environment, and it includes our policy. Okay. Now there's this funny thing. It seems funny, but before we had a graphical model for constructing, for sampling from the MDP, and that graphical model had this in it, multiplied over all time steps, and it had this in it. Just say there was a prior on the actions that were allowed, there was the state transition probability, and there was the initial state distribution. And what we've added to the graphical model is this, which is this silly made up optimality variable OT at every time step, right? But because it's Bernoulli distributed and always 1, we know that that's equivalent to this. So we've written down what the link function is. There's the link function, and this is always 1. So it's just, you know, that's the Bernoulli likelihood. But since it's always 1, we can just get rid of the likelihood. So this is the joint distribution of an optimal trace. We'll leave it at that.
Can I ask a question that's probably really silly? Why is the exponential in there? That wasn't in there in the original one, right? Like in the original, we just had an expectation over rewards, and here now it's an exponential over
Great. So we're going to get there in just a second. So like the critical thing to look at, and this is hinting, like what you really want to do is you want to look at like what terms are here and what terms are here. Okay. And so why is the exponential there? Again, we've set up the graphical model, and all I've said is like this is one of these silly things where we make it so, and then we demonstrate what results from that, right? Okay. So I'm making the graphical model so. Let's see what it does. Okay. Right. So if we condition in this graphical model, which is the same thing as basically setting them to equal to 1. But if you really actually do conditioning in this graphical model, right, then it's proportional to the joint. And the joint here, all it is this is the same thing. All we've done is pass the is like factor all of the reward terms out, right? Basically, the posterior over action. So in other words, we wrote down P O tau, and I should have, yeah. I'm trying to get away from you noticing one small thing, but it's not problematic. We wrote down the joint distribution. The conditional distribution of trajectories given optimality is proportional to the joint distribution, because things are always 1. That's fine. If you look at this, right, you've got this product. You apply this product to the exponent. You're just going to get the exponentiated sum of rewards here. Okay, and the rest of it is just as usual, right? So the point is that state action sequences with high cumulative reward are exponentially more likely than those without, if you just actually look at the posterior probability, right? That's true, right? Actions are the only things that we control, right? So the posterior distribution over actions that give rise to exponentially more likely states are going to be high probability under the posterior. Okay? So given our tools of inference, a reasonable, like sort of implicit policy, not an explicit, really represented policy, but one that you could just compute using the tools of inference, Hamiltonian Monte Carlo, Markov chain Monte Carlo, whatever, would be to choose the first action according to the posterior marginal over AT, conditioning in this graphical model on S naught taking some value and all actions being optimal. And then so on and so forth. So in other words, there's a nested inference problem here that's happening where we want to sample from the conditional posterior distribution in this model, okay? But, so in other words, right away in this formulation, you can choose a non-amortized, you can perform non-amortized action selection by performing inference in this graphical model at every time step. Just write down a new inference problem, run inference. Okay? And this gets to very interesting Prob Prog concepts of nested inference and like queries as program modules. But inference is slow. Can we use amortized inference, right? What happens if we find some phi star in Q such that that phi star is some minimum divergence distribution Q phi star of tau relative to the posterior distribution on trajectories, given that the optimality variables are 1 or true. And again, you know, min KL, we could just write out what the KL divergence is. And this is the same thing that we've seen over and over and over and over again, right? So here's the KL divergence between Q tau and this. If we replace this with the joint, right, we get the evidence of optimality out here, right, with a negative sign. That's fine. This has no phi dependence. So this is just the log evidence, and the minimum doesn't matter. You know, the minimum is constant offsets don't matter, so the minimum is invariant to that. This is more of an optimization person's way of looking at what the elbow is, right? Right. So the minimum of this is equivalent to the minimum of this, and if you squint at this, this is equal to the maximum of the elbow. Just put a negative sign on this, that affects the log. This is the elbow, negative elbow. Okay. And voila, because we've made this graphical model, so basically finding a phi that minimizes, you know, this divergence is just the elbow. Okay, that's fine, right? But it gets more interesting when we actually write out what these terms are. So if I just look at the joint of T and O over Q phi, which is just the inverse of this, right? Then this is the log joint over Q. And I told you to look carefully at what terms were in, and I'll even try to use the same colors maybe, what terms were in P. I think I got the colors backwards, but it doesn't really matter. And what terms were in Q. Right, and what you'll see, don't have to look very hard, is that this distribution cancels, all of these cancel, and what you're left with is the sum of log x per ward minus, and this is still in the sum, the log of the difference between pi phi and pi naught, where for various reasons we've switched that to a negative. Doesn't really matter. Just turn it over. Right? Log x to the reward is just this, right? And this says that maximizing the elbow is the same thing as in expectation. Remember, there's going to be an EQ on the outside of this, EQ tau, and there's going to be an EQ tau on the outside of this. This is the same thing as maximizing the cumulative reward plus some funky terms. Right? So that's all we have here. In one page, right? This, if we minimize the scale divergence, given that we've made this crazy graphical model, right? That's min5 minus expectation over trajectory rollouts, which is max elbow, where the thing that, like this elbow, the thing that we've been looking at and confusing you about for several lectures, right? In the RL case is just the expected reward ahead, the cumulative reward ahead. So if you really actually look at this pretty carefully, right, you'll notice that, like, yeah, I mean, you can stare at this long enough and see what's going on. This looks like a likelihood term, but directly on the trace, right? So this means that amortized variational inference of the exact time we've talked about learns a policy parameterized by phi, which corresponds to an entropy regularized policy, right? So if you've heard of like soft actor critic or something like that, the soft comes from this, right? That maximizes the expected reward ahead at all t, right? That's the first part of this. That's this part, right? If you take this sum and move it over here and then compute the expectation over q, what you'll see is that, particularly if basically you have no prior belief about what actions you should take, you just have a uniform over some bounded interval, right? Then the last bit is equivalent to basically maximizing the entropy of the policy summed over all time steps. Okay. And this is generally thought to be good, like policies with high entropy explore more than policies with low entropy. In other words, at every state, you're more likely to have a broader selection of actions that you would consider. This can be good or bad. You know, if you really want to solve to optimality, you want to get rid of this entropy term because you really want the policy to zero in on exactly one action to take. But in practice, this like entropy bonus, which I hate this terminology, but it's a policy entropy added to the reward, so it's a bonus, leads to better learning of dynamics.
Can I ask a question?
Yeah.
Can you just like compare this elbow that we use in RL with like the VAE elbow, in the sense that reward is sort of like maximizing the likelihood, and this entropy bonus is sort of keeping your approximation Q close to the prior? Is like, are those the same equivalent terms?
Yeah, basically.
Okay.
Yeah. So there's this funny thing that as you do probabilistic inference and you become a Bayesian believer, like you go through this like several phases of intellectual development, which I'm trying to push you all through very quickly. One is like, Bayes is awesome, inference is cool, you can solve all sorts of problems, but then you get to this thing where you're like, well, what's the likelihood function? What should the likelihood function be? What's the model, right? Then you realize that the likelihood function is kind of arbitrary, and that's kind of the same thing as reward. Like who knows, right? You write something down, right? It's some loss, right? And I'm okay with that. That's basically what this is. That's what there's some reward. It's like you can mix rewards and likelihoods and whatever, and at the end of the day, it really only matters what your task performance is. So this is where we go back to being like really hardcore machine learning people and say, screw it, all this formalism doesn't really matter, but cool, we can write down interesting losses, and because we have these interesting losses and like there's been 70 years of work on inference algorithms starting from trying to develop the hydrogen bomb, right? Like maybe these give us ways of thinking about solving these nasty optimization problems, right? Okay, I'll just say all the marginal conditionals of the posterior are matched when the gap is tight, right? And you should note this derivation, right, whatever this thing ends up being here, is model free in the sense that there are no remaining because of the fact that they cancel out. There are no PST plus 1 given STAT terms here. We chose P and Q such that these cancel out. So we can actually optimize this without having a model of the world, because all we have to do is interact with the world when we roll out under Q. We literally actually go out and run our robots in the world, and they do whatever the hell they're going to do, right? Given that we supply various actions to them, right? Okay. And if you really squint at this again and you say, actually, the environment is really actually deterministic, again, if you go back and look at this, then this expectation really isn't an expectation anymore, because the transition dynamics are deterministic. The only thing that you're searching over or you're taking an expectation over are your actions, in which case you might as well just search for the sequence of actions that maximizes the reward. Okay, so we've made it quite a ways. Not all the way I want to get to, but at this point, and this is a good place to take a little snack break. At this point, we can frame RL as inference, and we can select actions when we're in a particular state in a couple of ways. One, we can be slow, and we can run a traditional inference algorithm, like when acting to compute the full posterior over optimal paths and then select the next action by choosing it from the marginal of the resulting posterior distribution arising from conditioning on optimality in the graphical model. Or we can go fast and we can learn an explicit policy beforehand via amortized inference. Okay. If you want to take a couple of minutes to go pee or eat something, we can. Otherwise, we can keep going. I think we'll take 3 minutes. Take 3 minutes, run to the bathroom, grab something to eat, and we'll be back at 4:38. And we're back. Okay, so where we can frame RL as inference now, that's cool, and we can select actions via slow inference and fast amortized inference. We have 19 minutes or so left. So let me just connect what we're talking about to like real RL algorithms rather than RL as inference algorithms in just a second, and highlight a problem that I tried to highlight for the purposes of problem definition or final project choices. In what case? So in the accompanying lecture notes, there's a rather involved and a slightly tricky proof of what is basically the policy gradient theorem, but it's basically the same thing. Where the gradient quantity that we were just looking at, which arises from maximizing the elbow or using gradient methods to maximize the elbow, can be rewritten in the following way, and you will not get this by just squinting at it. But the critical thing that you need to see is that the gradient goes inside the expectation, but more importantly, the expectation, so this becomes a sum over time steps, where the expectation is over future trajectories from whatever the time step is. Okay? Which, importantly for semi-practical RL algorithms, moves this expectation inside so that the expectation is relative to each time step. In other words, if you look at this T also, this is, the future reward from whatever time step you're in, okay? And this moves us a little bit away from Prob Prog because you can't do this in the general Prob Prog context because we don't necessarily have the Markov structure that you need in order to derive this result. But that's an interesting problem to think about as well, okay? So this is a little bit difficult to do on slides, but in particular, I want you to think about this, splitting this expectation here into the expectation over AT-ST and the expectation over the rest of tau minus AT-ST given AT-ST. That you can clearly do, right? if you do that, then you can look at this interesting quantity, which is this expectation here, which is the expectation over, given that tau t is ATST, the remainder of the trajectory, this future reward, cumulative reward, plus these funky terms, which is the soft bit of soft actor critic, right? Let's define this as the Q function. It's going to be basically a soft Q function, but that's fine. Soft. So this is a Q function, which is the expected reward ahead following policy pi phi, starting in state st and having taken action at. That's a thing that you can think about, right? So all I've done is plugged in what I just said. So I've split the expectation exactly as I said, and then identified this bit as the Q function. And this now is going to look a lot like something that you would see in modern RL, which is that there's some gradient, and sorry for putting JQP here, but there's reasons for that. It's just that this is our objective, forget the QP bit right here, which is just going to be the sum over a bunch of states of an expectation over STAT of the gradient, basically of the gradient of the score function here, times this Q function. Okay, and this is pretty cool. This is basically a modern RL objective, right? And then the question becomes, how do we estimate this Q function? We know how to estimate this. This is straightforward. This is just this is a standard score function thing you've looked at 100 times, right? And then there's a question of how do you actually draw samples from this thing? And that gives rise to a whole bunch of different algorithms, right? So like how you estimate this thing is basically the stepping off point into all of the modern actor-critic methods in RL. So lots of approaches involve like rolling out under the policy number of times, then resampling actions at every time step, right? So in other words, you can think about this as being an expectation over some replay buffer where you go along your experience, basically sampling ST from the sequence and then sampling AT condition on ST from your policy, and then updating your policy according to this Monte Carlo estimate computed by this. Okay. Or maybe more importantly, if you maintain some parametric estimate of this Q function, so in other words, if you're going to do that, so you can sample a trajectory, then sample along that trajectory, get an ST, then sample an AT condition on the ST from your policy, then you have to compute this gradient. That's totally fine, but you have to multiply it by something, right? And in order to multiply it by that thing, you have to actually estimate that Q value. So you can estimate that Q value by an empirical estimate computed from a buffer of rollouts. Or you can run sequential Monte Carlo to get an evidence approximation there if you want to, if you can restart your simulator or whatever. So now model-free, model-based RL starts to get conflated a little bit here. But the critical part is if you only have real-world experiences, then and your state space is continuous, then this thing, if you do an empirical estimate of Q, will just be your expected reward ahead on that particular rollout trajectory. And that's what you use as your learning signal. Okay. Alternatively, and this is sort of really modern RL, if you have a parametric estimate, and I think this should be Q psi. Sorry, this is a mistake on my part. If you have a parametric estimate of this Q function, then you can just plug in the value of that estimate here, right? Fine. And I would argue that for Prob Prog and for RL, estimating this this Q function is the single most important problem. Like, what's the value, what's the expected reward, cumulative reward ahead, right? So one way of estimating Q arises from looking at the definition of Q and basically writing out the Soft-Bellman updates, which is that if you just, this is what we define Q to be, right? But in this particular formulation, AT, ST is fixed, so we can actually pull those out of the sum, and those come out here, right? Which gives us an expectation over everything that's left in this sum here. That's totally fine. Then you can factorize this expectation into an expectation over the next state, given this current state, and the action in the new state. If you collect the stuff that was in here, this is referred to as the value function. And if you split this expectation like in the way that I just did, then this gets you to a recursive definition of the Q function, right? So in other words, the Q function at ST plus AT is the current reward plus an expectation over the value function or an expectation over the Q function when you're sampling A, S, and A. Okay? And this insight, this sort of fixed point thing, you can set this up basically to be a fixed point in that equation, and this is what modern RL does to learn the Q function. So in other words, if you parameterize this Q psi here, then you can attempt to minimize the difference between these two estimates, right? Because you actually have these values, right? You have these from a replay buffer, and you have this from your policy. And you can attempt to do exactly that. So you can learn your Q function parameters psi by minimizing in expectation over ST-AT, replay buffer policy, the difference between your estimate, your estimator's output at ST-AT, given the current value of psi, and what it should be, given its definition, where its definition includes itself in the future. Okay. So RL, we'll take it as given, is a sensible way to frame artificial intelligence, decision-making, action selection. Reinforcement learning as inference frames reinforcement learning as a state space model with optimality variables. Amortized variational inference in this model produces a policy. This connects RL to inference in the world of model-free policy grading algorithms, right? And the only only specific things we've talked about are that the Markov model-specific policy gradient theorem breaks apart the expectation over trajectories into expectations that allow some amount of learning to take place without further interactions with the environment, right? And just to try to make that somewhat clearer, right? You can continue to evaluate this without actually having to go out into the world and gather more trajectories. So you can gather a bunch of trajectories and then actually update your policy using this without having to go out and interact with the environment more. Because the expectation over here is only over things that are in your policy or can be sampled from a replay buffer because you've broken the experience down into individual components. But it means that you have to be able to estimate this Q thing. And that's hard. Okay. Last couple of minutes. Thanks to Baron for putting this together, right? The missing homework number 7. The thing that ties it all together, that makes it worthwhile, the reason why we were all in this together, right? It's a silly problem, but it's very telling, right? So like, let me give you a maze. Let me give you a random maze. You have a generative model over mazes if you want, right? Can you navigate from the square down here up to here? How do you do that? And of course, you can use a search algorithm. This is just meant to be, like, let's not do A star, right? Let's use the tools that we have. How do we do this, right? So the missing homework number 7 is frame this, write the actual HOPL or FOPL program to do this, right? So frame it as slow inference. Theoretically, now you should be able to do that. Then use amortized variational inference to learn a policy for doing this. And then the most interesting bit of it all is that at the very end, you should be able to do amortized variational inference. One can do amortized variational inference to arrive at a policy that immediately acts optimally given some new maze. One way of thinking about this is that this is a way of learning and a stupidly efficient heuristic function for a search algorithm, right? In using all the tools that we've gotten. I see that at least one person's eyes are flicking up now thinking, oh, wait a second, actually. Yeah, so if you're doing search and you want to be able to amortize, you can, if you want to learn a heuristic for search, that's the same thing as amortized inference, amortized variational inference for reinforcement learning. It's exactly the same thing. Okay. Cool. So how do we do it? Well, the first question is, can we write it down as a FOPL or a HOPL? So, again, thanks to Baron for, humoring me and actually writing these programs and actually running inference in them, right? So you can write it down. Here's a map, right? There's some maximum number of steps that we would want to consider. So we can compute a loop bound, right? There's some state, which is the initial state. In this particular case, I don't think it's actually on the map. Oh yeah, which is the initial state? Is it this one, Baron? And we're trying to
I think it was -2, but or -2, but it's like.
Well, it doesn't really matter. Yeah. Okay. And we can write a loop that maximally visits a certain number of states and, iterates. And what does iterate do? Well, we could read this. It doesn't really matter. It's sort of obvious what's going to happen, right? You're going to draw a sample from your default policy, and then you're going to observe optimality, and you're going to keep going, right? So in other words, you're going to sample from your default policy, try all directions uniformly, keep going, and at every step, you're going to observe this optimality variable, which will accumulate whatever the reward is given your state and the map. Okay. So an interesting question, which I learned something about while we were doing this, which is that if you try to run this in the FOPL, you run into an interesting problem, right? So here's one thing you'd like to be able to do. You'd like to be able to it's simple, just a few steps through a maze, right? If you write this in the FOPL, the sugaring pass from Daphne, this is basically the number of steps that one must look. The number of steps one would consider, right? The desugaring of the program, the compiled program size, or desugared program size is really probably what they should say, grows exponentially. Whoops. Okay. So this is yet another reason, again, more justification for all the pain of the HOPL stuff that we've been looking at. Okay. So if you actually want to frame and solve an RL problem as inference, you need the HOPL language facilities. So you can write the same thing in the HOPL. Here, the program is written slightly differently, and you need to go between a start state and an end state, which are specified here. Now we can use recursion when we step until final, because we have the facilities of the HOPL, right? And as you're sampling from the default policy and transitioning according to that sample, at every step, you observe under this Bernoulli distribution here labeled flip, some reward that depends on whether you're in the final state or you're stepping towards it. And again, we're abusing the type system and saying that flip will accept real arguments, not arguments between 0 and 1. Jason. Okay. And if you do this, and you run this, you get solutions. And I didn't push Baron to go all the way to the amortized inference or the meta-learned objective, but this was one of the potential final projects, right? You get a posterior distribution over trajectories that finds the minimal length path in this maze. Okay. And somehow, what I would really like to do is start the entire course with this, right? But we have to get here, and then we can actually jump off and start thinking about how these tools are really wildly useful. So that's it. Reinforcement learning is about learning policies or controllers that maximize reward. Selecting actions that maximize reward can be framed as posterior inference. That means we can bring all of our inference algorithms to bear, right? FOPL language utilities are too weak to express RL problems. So amortized inference in a HOPL program is equivalent to policy learning. They're really basically part and parcel of the same thing. And the Markov structure of the MDP is exploited in mainstream RL algorithm developments, in particular in the policy gradient theorem. Things that we didn't talk about, and I wish that we could or did, but are very close to research, so it's very difficult to write lecture slides for them, but and there'll be projects on this, and we can turn them into slides next year. So sequential Monte Carlo and reinforcement learning, there's a really close connection, right? Because obviously we're doing inference, like we needed to explore the entire space in order to get the evidence of optimality. So there is a tight connection between Q function approximation and heuristic weights to be applied in optimal SMC algorithms. We didn't talk at all about model-based RL, and that's a whole can of worms. Where you actually learn the state transition distribution as well. But you can see where we talked about amortized inference, and we specialized in amortized inference, and then we talked about model learning in the context of amortized inference. Same kind of story applies here, right? If you want to learn the model of the world, then that's now model learning in the amortized inference framework setup. So it's just a big structured VAE. There's a bunch of thought that's gone into using advanced SMC algorithms in RL, but basically nobody's actually done it. And this is, I think, really exciting, particularly IPM-CMC is a very powerful algorithm that should be considered in this context. And the flip side has been considered by very smart people, including Hong-Suk, my friend and former frequent collaborator, where generalizing the Q function approximation idea in the context of general purpose evaluation-based probabilistic programming inference is a very interesting avenue for future work. So there's a bunch of papers at the end of this, but also the lecture notes have a bunch of references if you are interested. So thank you very much for your time and attention. And yeah. Questions? Hi, Payman.
So maybe I can ask a question. We talked about this, and I should probably know the answer to it. But in the if you want to do amortized inference for that simple example that you just showed, would you amortize over different maps? So you just show a map, find and then do your variational inference over with taking the sort of map as a conditioning variable?
Yeah. So when we do yes.
Okay.
So it becomes so amortized inference becomes meta learning when you average over something, generally speaking, the context. And the context in this particular case would be the map.
Mm-hmm. Okay. Yeah. Okay. I think I understand that.
Right. So your policy becomes map dependent, right? Rather than.
Yeah.
And again, this is right at the cusp. So what I've done, if you've hung with me, I've delivered you to the cusp of modern RL, Prob Prog, amortized inference, meta learning, all kind of at the same time. It's been painful at points, but we're there, right? You should be able to think about all this sort of stuff. Now, at least through one lens, and that lens is, of course, meta learning, amortized inference, variational inference in a graphical model corresponding to whatever it is you want to do.
Yep.
More questions?
How would you actually do the model learning? So the transition dynamics function, because it seems to me if you have a replay buffer, it's already kind of a model learning in a way, right?
Yeah, I mean, so if you think about yeah. So there's, unfortunately, just to be clear, there's a huge amount of complication in this RL framework setup thing, right? It's really, it gets hairy real fast. But the critical bit is that this is theta, right? And when you're doing variational, like if you're doing optimization in a variational autoencoder, right? In some sense, when you generate samples from Q, so there's an expectation around this about Q, right? When you generate samples from Q, learning this becomes maximum likelihood. Like literally, it's like a regression problem, because indeed you have effectively some set of samples, and now you just need to fit this conditional density, right? And that's, you have all parts of it. You have ST, you have ST minus 1, you have AT, just fit it, right? The problem is, and this is where RL becomes a different paradigm to supervised learning or unsupervised learning or so on and so forth. The problem is that the real question is, what Q do you actually roll out under? And that's where things get a little dicey, because if you roll out under your model, you cannot explore, right? Or the places that you will explore are going to come from some model that you've trained. You have no idea where you're going to explore, right? Because the thing that we're conditioning on here are these optimality variables. That's the thing that we're conditioning on, right? So everything else is a total fabrication. You're not conditioning on some set of observations or some, like the rollout is, you're just making up data. So if you make up data and then you fit your model to made up data and you then roll out under made up data, you can get yourself into sort of perverse situations where your learning just doesn't work. That make sense? What to do about it is an area of active research. That we can have this conversation is a success.
Is something like wake sleep sort of sounds like that, right? Like where you do some updates under the model and some under the real world. Like is that something that would, I don't know, have something to do with that, or is that completely?
So the real issue is just to remember that this is the definition of Q, right? And you either have a choice of using p theta here, or you have a choice of actually rolling out on the real world. And that's not quite the same as like wake phase sleep updates, right? We're, again, the only thing that we're conditioning on is it's even hidden from Q, right? Literally, this is made up, 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 this is made up. The only thing that we're conditioning on when we're doing this, if you think about it, right? This is QT given O. That's really the variational inference problem that we're solving, right? So condition, like condition, like putting O in doesn't do you anything, like, but you can do semi-supervised. You can have, if you have exemplar trajectories, then there's ways of thinking about doing semi-supervised learning here, right? That's totally fine if you know that these are optimal trajectories, but you don't know that they're optimal trajectories. It's hard. It's just basically a hard problem. Even to write down formally is a very hard problem. Naomi, did things come together?
A little bit. I think I didn't follow as much after the break.
We went very fast after the break, but the main point was that the thing that I want to make sure that you get, really the number one point is that all of the stuff that we bring to bear, all of our inference algorithms can be brought to bear on this problem. But the question that you really had was like, what's going on with these optimality variables? Hopefully that's clear. That's the part that should be clear. Like, put these optimality variables on, the thing turns into an inference problem. That's the that's the take home from today. All the extra bells and whistles are just ways that you can go off and access the literature from this perspective.
Yeah, I definitely understood that part.
Okay, I just want to make sure that landed. Right?
Yeah.
So is it like the best way to cast the problem as inference, or are there like competing alternatives?
I think it's pretty good. I think it's the way it's natural and basically correct. Yeah. This has been around before, Sergey. So Bert Kappen at Nijmegen has been talking about control as inference for a very, very long time, and it basically uses the exact same optimality variable setup and linear dynamical systems, and where you can actually compute things in closed form. And yeah.
So is there any intuitive description that distinguishes the soft Q function from the Q function?
Bear in mind that there's like a non-trivial chance that what I refer to as a soft Q function is different to what the RL community refers to as a soft Q function. They have so many different terminologies that I get lost. I think the intuition that I was trying to get at, and the only thing that really I'm after, is that the reward here, the reward has this extra stuff on it, the entropy bonus, and that entropy bonus has a bunch of terms in it which are the entropy of the policy. So it says, I would prefer, everything else considered, everything else being equal, to have a policy that gives me more options.
I see. So you're like modifying your reward to favor high entropy policies.
Higher entropy policies, yeah.
Would that cause trouble when your reward is too small and then the entropy bonus becomes too big?
Again, this comes back to your question of what is reward? What should the units of reward be, right? The relative strength of this versus this is controllable in a lot of ways, right? If you make your rewards particularly aggressive and meaningful, then this is basically irrelevant. It doesn't matter, right? But this is also true when you think about likelihoods, right? When you're doing regression, you can make your likelihood mean a lot by setting the variance of your observation distribution to be something very small.
I see.
Right? And the same thing is happening here, right? As you make your observation variance larger, right, you're going to get smoother, less interpolating, less. the prior is going to dominate, right? And that's what's going to happen here. And that's totally reasonable, right? It's just, in fact, in some sense, it totally makes sense, right? If you don't have a lot of reward, you don't have a lot of information about what's optimal, right? Then why should you default from just your default policy of do anything that's allowed? Right? So I think that's totally fair. Okay, there's no more. I really want questions. This is fun. This is fun to talk about. I really want questions. But if there are no more questions,
I can ask another question if you.
Yeah, please. Yeah, let's do it.
Can you spend like half a minute saying something about these more sort of fancy SMC methods for RL?
Well, the 30-second version is I guess we haven't done the tighter bounds lecture yet, but the give me some space somewhere. Oh, I remember how to do this. No. I've done this with you a couple of times, I think, but this is not going to be 30 seconds. The point, switching back to sort of standard SMC / whatever, when we did SMC, we had these weights for a particle K. We had, samples of these guys. And this was the weight that we computed. Right? And when we did inference compilation for higher order probabilistic programs, we said that we wanted to learn a proposal distribution for conducting and directing the program that took all of the observations. And remember, in the RL context, you could just switch Y to O and X to everything else. Right? When you propose from this, the weights that you get are not optimal. What you want is a set of weights. You have to, your optimal weights arise from proposing from Y1 to little t. Okay. So it can be established that for SMC, the optimal weighting under the sequence of distributions that arises from evaluating or forward execution of the program, the optimal weights that you need to apply go to little t, not to big T. The proposal mechanism needs to be that. But in order for your proposal to be good in the global sense, you really, really want to use this proposal. But in order to make the weights optimal, what you want is, in effect, to pretend as if you're proposing from this. And the way you do that is you have to introduce up here what is equivalent to the Q function. And it's going to take way more than 30 seconds to derive this. But these become equivalent if you have the Q function that we just looked at, or it depends on how you write it. It's the value function of the Q function. They're basically the same thing. This factor up here appears. So the question is, if you run a super fancy inference algorithm for, talking about Greg's idea about doing model-based RL, or even policy learning. In order to do any of those things, you have to explore efficiently, and you have to basically characterize the full evidence. In other words, you have to experience like the full distribution under optimality, right? Effectively, you're collecting paths under optimality. And the way you get those is by conducting your inference by actually following optimal paths, which in the amortized case you can get with a proposal like this, but sequential Monte Carlo will kill you because your weights will be totally imbalanced. So you have to introduce these factors, but these factors are the Q functions, which means you have to estimate the Q functions. But when you're doing iterated sequential Monte Carlo, you're allowed to use whatever proposal distributions and heuristic factors you want, so long as you're actually running sequential Monte Carlo. You still get a valid like normalization constant estimate, which means that you should be able to interleave sort of generations of IPM-CMC with gradient estimates of both Q phi and your value / Q function estimates. And that's a whole different way of going about RL. Basically, it's saying like, it's one way of looking at it from the RL perspective is that IPM-CMC like manages your replay buffer. And you will get better and better and better and better trajectories for your replay buffer.
Yeah, so this is in a sense like a good way, I guess, to learn this Q function and also small q.
Yep.
Is that right?
Yep.
Okay, cool.
I shouldn't have recorded that because that's a research idea, but yeah.
Just cut the video.
Yeah. You think I'm cutting these videos? Yeah, that's the, yeah.